In this video, I want to talk about an interesting and pretty famous problem in probability, and this is called the Monty Hall problem. Now, it's called the Monty Hall problem because it was presented in some form on the game show Let's Make a Deal. And Monty Hall was the host in the late 60s into the 70s, and I think into the early 80s. And on the show, so let's say Monty Hall problem, on the show, contestants were presented with a game. And in that game, they were given a choice to choose one of three doors. Well, I think in the show they use curtains. So you have three choices to choose from. You don't know what's behind each door. So we have door number 1, door number 2, and door number 3. And behind one of these doors is a valuable prize. I think in the problem, the way I presented it was a car. It could have been a pile of cash or some other valuable prize. And behind two of the doors, which were the losing choices, a goat or something, a coffee mug or some other inexpensive item. So you have one door containing a valuable prize and two doors containing a sort of a cheap parting gift. Now, the contestants are asked to choose one door. So you don't know what's behind the doors. You pick a door at random, and that is your choice. So let's say you pick door number 1. Well, before Monty shows you what's behind door number 1, he opens one of the other two doors to show you it's a losing door. So let's say you pick door number 1. Now, Monty knows where the car is, and if he opens door number 3, then the car is either behind door number 1 or 2. So there's two doors left. One of them contains the car. Now you're given the option. Before revealing what's behind door number 1, you are asked, do you want to stick with your original choice, with your original guess, or do you want to switch to door number 2? So do you want to go with your gut, or do you want to switch? And what I want to talk about now is that switching to the other door, as counterintuitive as it may sound, because it looks like right now there's a 50-50 chance because there's only two doors left, but switching to the other door actually doubles your chances of winning. So now let's sort of analyze this and sort of unpack the possible options. So you have two choices here. Let's say always stay with your original choice, or always switch. There should be a C in there. So if you stick with your original choice, so ignoring the whole switching business, so you pick a door, you stick with that door, you either win or you lose. Well, what is the probability of winning if you stick with your original guess? Well, there's three doors. One of them contains the car, so you have a 1 in 3 chance of winning. And the probability of losing, well, there's two doors that contain the prize you don't want, so we'll consider that a loss. And so there's a 2 out of 3 chance that you lose. So the probability of winning is 1/3, the probability of losing is 2/3. Now, let's look at what happens if you always switch. Well, so let's think about this first logically. If you choose correctly first, without knowing it, if you choose correctly first, so let's say the car is behind door number 1. You choose door number 1. You don't know what's behind door number 1. Monty opens up door number 3, and that's a losing door. And now, if you're always switching, you're going to change your guess to door number 2, and that's going to be a loss. Okay, so if you choose the right door first and switch, you're going to lose. But if you choose the wrong door first, So let's say your initial guess is door number 2. Well, now, one of two things is going to happen. So this is assuming. So let's erase this and let's erase this. So let's look at what's going on. Assuming you chose wrong, without knowing it, but let's assume you chose wrong. If you choose wrong, the car is either behind door number 1 or door number 3. One of those two doors, Monty is going to open. So if the car is behind door number 1, Monty opens door number 3, you switch, and you win. Or, let's reset this, or if the car is behind door number 3, that means, and you've chosen door number 2, that means Monty's going to open door number 1, and you're going to switch, and in that case, also you win. So, if you choose incorrectly first, you are guaranteed to win. Because the two remaining doors, one of them contains the car, and one of them Monty is going to get rid of. Which means, when you switch to that last remaining door, it has to contain the car. That's assuming you picked wrong first. So, to win, you have to pick wrong first. And if you pick correctly first, so let's repeat this over here. 1, 2, 3. If you pick, let's say, here's the car, and that's your first choice. If you pick the correct door first and switch, you're guaranteed to lose. Okay, so that's how you lose the game. You lose if you pick right door. I don't want to say right because right and left. Let's say pick correct door. Correct first. You're guaranteed to lose. Okay, so how many ways could you pick wrong first? Because that's guaranteeing you a win. Well, of those 3 doors, 2 of them are losing doors. So there's 2 ways to pick wrong first. So the probability of a win, which happens if you choose incorrectly with your first guess and then switch, there's 2 ways that could happen. So you have a 2 out of 3 chance of winning. And the only way to lose is to pick the correct door first and then switch. And there's only one correct choice out of the 3. So the probability of losing is actually 1/3. So you see, if you always stick with your original guess, you have a 1 in 3 chance of winning. And if you always switch, you have a 2 in 3 chance of winning. So you have double the chance of winning if you switch from your original guess. Now, there's another way you could look at this. It's a little bit more informal, but let's say you have these 3 doors, door number 1, door number 2, door number 3. You pick one of the doors. So let's group these doors into 2 categories. The ones you pick and the ones you don't pick. Right? So this is your choice. And so the likelihood that the car is behind the door you pick is 1 out of 3. And the probability that the car is behind one of these other 2 doors is 2 out of 3, ignoring the individual doors. Just this group of 2 doors that you didn't pick has the probability of 2/3 of containing the car. So that 2/3 is split evenly, 1/3 here and 1/3 here, but they add up to 2/3. Now, when Monty opens one of those doors, that 1/3 probability shifts over to the other remaining door. Still, in this group, there's a 2/3 chance that that group of doors contains the car. Whether that 2/3 is split evenly behind the two doors or it's a 0 for one and a 2/3 for the other doesn't really matter. Just from the beginning, your initial choice had a 1/3 chance of being correct. So this group of the other two doors had a 2/3 chance of being correct, which means if you switch your guess, you still have that 2/3 chance of winning. Yeah, and I think the first explanation made a little bit more sense from a probabilistic standpoint. But either way, there's other explanations out there. This problem is discussed in, I'd say, 99% of statistics classes that take place. This problem is brought up or discussed or at least mentioned in some way. Okay, that about does it for the Monty Hall problem.